In this video, we're going to discuss the double-slit experiment. This is a classic experiment that demonstrated wave-particle duality. What that means is that photons and other small subatomic particles exhibit both wave-like properties and particle-like properties at the same time. In the double-slit experiment, photons or other small subatomic particles propagate through two slits next to each other, which I'm going to label S1 and S2, and then those wave particles are detected over on another screen, and the way they propagate through the two holes implies that they have wave-like properties. So let's start the experiment off. We have a light bulb, and there's S1, which is the first slit. Light is propagating away from the light bulb, and some of it goes through S1. I'm going to draw what the wave fronts would look like as it went through. What that results in is, on the detector, a pattern like this, where most of the light goes straight through S1 and then hits the detector. Let's do the exact same experiment again, but this time we're going to open the second slit, that's S2. Again, we can draw the lines that represent the light propagating away from the light bulb. Some of that light makes it through the slit. Here's that light propagating through. And then if we graph the intensity distribution for that light on the detector, it lines up essentially with slit 2. So notice that when the light propagates through slit 2, it lines up essentially with slit 2. When the light propagates through slit 1, it lines up essentially with slit 1. What you'd expect then is, if you open both slits 1 and slit 2 at the same time to let the light through, you would simply get one peak that matches with slit 1, one peak that matches with slit 2. That's what you'd expect. In fact, what we observe is an interference pattern. We observe many maxima and minima, like that. So let's look at the explanation for that. Let's talk about what happens when both S1, slit 1, and S2, slit 2 are open at the same time. Let's draw the wave front of the wave particles, the photons, propagating through space. You can imagine this wave front propagating through S1 and resulting in the same wave propagation pattern out. At the same time, there's a wave propagation pattern out of S2. Now notice, on these two propagation patterns, there are locations where the two waves have maxima that cross. That would result in constructive interference, amplifying the size of the signal at that location. All of those are constructive interference. Those constructive interference events are reported as maxima over here on the detector. Notice that in between the places where the wave patterns cross, there is destructive interference, so there's less signal. And then there'll be another maxima due to constructive interference, destructive, constructive, destructive, and on, resulting in this interference pattern. What's incredible about this experiment is not only the interference pattern that's observed when multiple photons are shot through the slits, but let's imagine one photon at a time is emitted from the light bulb and shot through the slits. In a classical type explanation, in a Newtonian physics type explanation, the photon would have to either go through slit 1 or slit 2, and thus you'd expect the patterns we saw before where there's a peak associated with slit 1 and associated with slit 2. We do not observe that. Even when we shoot one photon through at a time, we still observe this interference pattern. The way that experiment looks is, let's say we shoot one photon and then we detect it, and I'm going to make a little X over here on this second detector, and I'm going to make a histogram out of it. So you shoot one photon through, you detect a photon incident on the detector over here, then another photon, shooting multiple through. As the experiment continues, you keep detecting the photons only at the locations where constructive interference is occurring, thus reproducing the interference pattern. And again, this is interference pattern just shooting one photon through at a time. The explanation for this is that the photons are actually wave particles. What this means is that the photon exists more like a wave in this region. So the photon actually does propagate through both slits at the same time, creating these interference patterns, but it creates all of the interference patterns we're observing right now. So it has wave-like properties, kind of propagating through like a ocean waves through a breaker wall. Once the photon in its wave-like state propagates through the two slits, it then constructively and destructively interferes with itself. Once it constructively and destructively interferes with itself, it then impinges upon the detector here. When that event occurs, the wave particle is forced to manifest its particle-like characteristics and appear as one of the discrete events, one of the discrete collisions of the photon, of the wave particle onto the surface. So this is a great experiment in that it shows both wave-like properties in terms of the constructive and destructive interference with itself, and at the same time particle-like properties in that one photon hits the surface at a single location in space.